Good morning. I would like to begin by thanking the organizers to give me the opportunity to present to you this recent work done at Yale University on artificial atoms, which fall in a somewhat side category of this meeting. The experiment is based on a very interesting proposal by Howard Carmichael. And I'm going to explain what this proposal is. In fact, it answers the question of whether quantum jumps, which are completely unpredictable in the long term, could have, on the short term, some degree of predictability. And the question can be reformulated in the following way. Is it possible to arrange things so that quantum jumps behave a little bit like tsunamis? As you know, tsunamis, although you cannot predict when they occur, it is possible to get an advance warning of their coming because the speed of sound in the Earth crust travels at the velocity of a jet, whereas the shock wave on the surface of water travels at the velocity of a car. So can we be in this kind of situation? And I would like first to acknowledge the team who has done the work. And this work is part of our effort at Yale on autonomous and continuous error correction. Much of the credit can be attributed to Zlatko Miniev, who's a graduate student who had heard this proposal at a summer school from Howard Carmichael, and who managed to convince me that this experiment, which looked essentially unfeasible, was actually possible and more or less really meaningful and not the repeat of anything that had been done previously. I would like also to mention Shantanu Mundana, who has made this ditransmon atom that we have used, and of course Shyam Shankar, who is helping me overseeing the work in the group. And last but not least, I would like to acknowledge also the long-standing collaboration that I have had with Rob Sholkoff and Steve Gervin. Okay, so this is the outline of the talk. I apologize in advance to the specialists and even the discoverers of quantum jumps who are in the audience. My review will be very simplified, but it is a necessary review to understand what we're going to do in these artificial atoms. So the story is the following. You are interested in a two-level system. This may be important for high-resolution spectroscopy. You have a ground state, a dark state, which is very weakly coupled to whose transition with the ground state is very weakly coupled to the electromagnetic field, and you want to detect this transition. And then there's this beautiful electron shelving amplifying scheme where you use this auxiliary level, this bright level, which fluoresces very rapidly. This is the so-called V-level configuration. So you have this first laser, which induces this very slow Rabi drive here between the ground and the dark state, and you reveal the transition in this manifold with a second laser, which cycles this transition. Of course, the necessary condition for such a scheme is that there should be a strict hierarchy of scale. This Rabi rate should be the slowest time scale, the rate here. Then this should be much faster. This BG Rabi rate should be faster. And then the fluorescence should be even faster. Okay, I'm sure most of you are familiar with this. And although there is a rather poor collection efficiency of photons in this experiment, it is possible to, through this cycling of hundreds of thousands of photons, to get the jumps between G and D, which are shown in the interruption of the fluorescence from B. And the reasoning is pretty much like this. So if you have a teenager, son or daughter who doesn't show up for dinner, it means that he or she is partying elsewhere. Basically, this is the counterfactual reasoning, which allows you to attribute this dark period where you see no fluorescence to the fact that the atom is jumping to the dark state. Now, of course, these quantum jumps are omnipresent not only in atomic physics, but in condensed matter physics. I would like to note here, mention the beautiful work of the Arosh group on the quantum jumps of light. They've been seen, of course, also in this beautiful work on nitrogen vacancy center in diamond, and even in atomic, in Andreev levels in atomic point contact. But what interests me today is the how they manifest themselves in superconducting circuits, quantum circuits. And here I would like to point out that there have been previous works on quantum jumps that have been observed since a number of years, but the work always was dealing with only two levels. And here, the third level is absolutely crucial. It is it's the enrichment of the Hilbert space by the third level, which allows you to make measurements which are going to have this advance warning. And now I review the proposal of Howard Carmichael. An essential condition is that the measurement, the amplifier chain, should be fully efficient. So not only the photomultiplier has to have a quantum efficiency of 1, but there should be no dark counts and no dead time. And also, there's this condition that the bandwidth of the photon detection should be even faster than the time between jumps. And under this condition, then the arrival of the photon are delta function peaks, like shown here. They have Poisson distribution, but this Poisson distribution is interrupted. So you see you have two types of jumps here. You have jumps associated with the transition from G to B, but there are outer jumps where these inner jumps here stop, and that constitute the transition to D. And that's what we are going to study here. Now the question is, can we focus here on the time just after the last click here, the last photon, and see the jump rising, see the flight of the jump? In quantum trajectory, this is something that has a sense. So from the measurement record, since the measurement is fully efficient, the observer has access to all information on the system. The inferred wave function of, or the inferred state of the system, is pure. You can talk of its wave function, and from this wave function, you can compute the population of the ground state, which is essentially always populated because the emission is very fast of the photon. So you have only a small probability of being in the bright state. And if we take this last click here and we follow it, we see that there is a beautiful latency period during which the jump is not occurring yet. It occurs continuously here and evolves smoothly to the dark state. I would like to mention that the Rabi drive here is so slow that basically the arc of sinusoid that you would see if there would be no observation, if the system would have a unitary evolution, well, this arc of sinusoid would have a maximum outside the building. Okay, so what is remarkable here is that this curve is deterministic, shot to shot, And the middle point here has a well-defined expression here. And for those who think that open quantum systems are just a variation on a closed system, well, it's not so easy to find this logarithmic factor here. So the prefactor is basically the average distance between jumps, but the logarithm factor is what creates this latency period. If you can manage to spread all these time constants over several orders of magnitude, which we achieve in our experiment. But the really fantastic thing is that if you take this middle point, well, you have a quantum superposition of G and D. So not only the jump evolves continuously, but it evolves to a coherent state. And this is really a wonderful prediction. We'll see more about this coherence later. Of course, this is a very delicate phenomenon, because in order to observe it, you should not miss a single click, because missing a click means that you are going to introduce a temporal fuzz here, jitter, in this data, and you're going to wash out very quickly this coherence. Okay, so how do we do this? Well, we use this basic superconducting circuit architecture in 3D. This is also known as circuit QED. And it uses a circuit. The artificial atom is just a Josephson junction shown here with two pads, which forms a sort of dipole antenna. And this chip is housed in a superconducting aluminum cavity here. And what is remarkable is that this system, although very macroscopic and almost dirty in some sense, obeys very exactly or very precisely this kind of Hamiltonian. At least these are the first order terms. And where you recognize here the excitation, the C is the excitation of the annihilation of photons in the cavity, and B are the annihilation of excitation in the atom here. You have this nonlinearity which characterizes the atom. And here you have a cross-coupling between the number of photons in the cavity and the number of excitation in the artificial atom. Here, we're not going to use this previous simple transmon. We're going to use what we call a ditransmon, a sort of transmon molecule, if you want, which has this structure here. We have two strongly coupled transmon. One is oriented along the cavity field and will be responsible for this bright transition in the system. And the other transmon is oriented perpendicular to the field and is responsible for this manifold that we are interrogating. This is a perspective view of the chip in the cavity. You see how the various dipoles are oriented. And I would like to mention that although these two transmons have four basic levels here, the various this strong interaction between this pad here takes this fourth level and brings it completely out of the picture so that we can ignore this level structure and concentrate on these three levels. For the specialist of the field, there are some constants here, which shows that the transmons are pretty standard. An important figure of merit is the decoherence time of the DG transition, the Ramsey time, which is that of a state-of-the-art transmon, 120 microseconds. I would like to mention that the slowest time scale in the system is a few nanoseconds. That's the speed at which we can measure the reflected signal from the cavity here. So we have this fast electronics which sends a pulse, a readout pulse to the cavity. The pulse is reflected. It's amplified by this quantum limited Josephson parametric amplifier, goes through a ramp, and then it is analyzed in real time so that we are going to, depending on the signal that we get, we are going to detect this dark transition, and then we are going to react in real time. There's a feed-forward loop here, if you want, and we're going to stop the system when we decide that a quantum jump is about to occur. The way the readout functions here is the following. So I have inverted the diagram. The ground to dark transition here is on the left here. So the question is, how have we managed to have the equivalent of detecting every photon in the original quantum jump experiment? In fact, detection overall from beginning to end efficiency is 90%. So the experiment is as if in the original experiment we had detected and measured with a very large bandwidth all the 90% of all the photon. And this is achieved by inserting another amplification stage. So instead of detecting the fluorescence of this bright state, we dispersively measure the population of this state. And this is done in the following way. So we have this coax cable here, which brings a microwave pulse to this resonator. And this schematic here shows that the resonator has a frequency, a resonant frequency, which depends on the state of the system. It has one frequency in the bright state and essentially another frequency where when the system is either in the ground or the dark state without being able to distinguish between the two. This is shown here. This is the cavity response if you are in the bright state, and here the responses of the dark and ground state essentially overlap, so that if you send your probe signal here, right on resonance, you cannot get information on whether you are in D or G. This is why this measurement is called B non-B. And the amazing thing is that this projector on non-B commutes with all the operators in the G-D manifold, which is a sort of super QND measurement, if you want. There is some details here which I'm not going to go into, but there is, of course, the rabbit drive, which we can vary here between G and D. And for the bright state, we have to have two frequencies to drive it. If you are interested, I will answer at the end why we have this detail. The important thing here is to observe the scattering of all the time scales. There are 5 orders of magnitude between the slowest time scale, which is the Rabi time here, the time it takes to complete a Rabi oscillation between G and D, and the measurement of the B level, the time at which the measurement rate of this B level. This measurement can be fast because we're using about 7 photons in the readout cavity to obtain the information. And this is what an heterodyne analysis of the response of this probe signal gives you. You see, you have information essentially in the main quadrature, the I quadrature, but there is also some information that we collect and use in the Q quadrature. And you immediately see that we have the same kind of data as in the ions. We have this period here where the photon number in the cavity varies, and then there is this period where there's essentially no photon in the readout cavity. We can do, of course, better. We can do an assignment of the system. Here, this is a very raw assignment. And all these assignments that I'm going to show are possible, again, because of the fact that the timescales are spread over a large, many orders of magnitude. So let's go in detail on how we determine the state of the system. So from so at each instant of time, we detect an I and a Q measurement, and this is analyzed in a quadrature space. And if the data lies on the right here or above, we declare that the state is B. And if it's far on the left here, we can be confident that it's in G and D. And if it falls in the middle, we just keep the same point as before. And with this two-point filter, we can assign to the data in real time whether the state of the system is rather as a majority B or D or G. And the transition from B to G is indicated here by a down arrow, which is essentially it would be the equivalent of photon event that would be that you would get in the original ion experiment. This is just to facilitate the understanding of this period here, where the system cycles between B and G. But you're not detecting the fluorescence; you're just measuring the population of the state. Here, it's translated into a sort of equivalent fluorescence signal. Okay, so now we're going to zoom in and look at what happens on the last click, just after the last click. And this is where this fast electronics is going to be important. Let me mention that we have a good separation between the time where you essentially transition from G to D and back, which are these interruptions, and the time here between cycles of the photon. Thank you. So this is how the electronics here works. We detect a jump down here of the B to G, and then we start recording whether there is an absence of a jump back to B. And we wait a certain time, so we condition the data on the observation of no clicks, if you want, and at a certain time, we declare that we are going to catch the system. So when we catch the system, we stop all the drives, and we do tomography. And this is the result of the tomography. This is the Z measurement, a Z operator measurement of the equivalent two-level system of DG. And you see that it obeys a theory very well. The theory is what? Well, the ideal theory, if everything would be perfect, this curve would be a tanh function. Here, we don't reach the population doesn't reach exactly 1 because of these missing events. We don't collect all the events, and so there is a slight miss in the population. But what is most important is the coherence. So the X component here is the coherence, the superposition between G and D, oriented along the DG drive. And you see that it reproduces very well the ideal theory. The ideal theory would be a hyperbolic second, or 1 over cosh. And it should go to 1. Here, it doesn't go to 1 because, again, of the fact we don't detect all the events. As I said, we are very sensitive in this experiment to missing events, so there's a drop. The drop is also due to the fact that the coherence of the atom is not perfect. That also introduces some loss. And it also shifts the maximum here with respect to the middle of the jump. And now I'm going to focus on this coherence that we get here. By the way, I want to also mention that the theory, which it takes into account all the imperfection of the system, predicts this overshoot, and which is due to the fact that this drive here is not infinitely slow. So there's a bit of negative coherence that is observed at large time. So what is this coherence here? We have a measurement, and then we find that the jump is coherent. Well, you might say, but you're driving after all the system. We have this view of this drive which is on. Well, we can stop the drive. We can, before we reach this maximum, we can stop the drive. So now the system is free. It's only submitted to the measurement. And yet you see that the coherence increases. So we have this paradoxical system, just 1 minute, and where actually the measurement, the fact that the system is open and in contact with the measurement apparatus produces an increase of coherence. And what happens is that basically the initial information on which circle of the Bloch sphere the system evolves is given by the drive, but only at the beginning of the jump. It's not necessary. Once you have induced this transition, then the jump proceeds only through the measurement. Okay, this experiment shows that we can reverse the jump by a pi over 2 pulse. Here, this is the angle by which the pi over 2 pulse is applied. You see that we can both actually reverse the jump and also actually complete it. Okay, my time is up, so I will just point out my conclusion slide. Just mention that actually this experiment is interesting from the point of view of fundamental quantum measurement, but it's very important also to efficiently do quantum error correction when you are measuring error syndrome in a continuous manner. This analyzing, if you want, the detail of the birth of the excitation is very important to fully efficiently correct errors in computation and sensing. And on this note, I would like to thank you for your attention.
Thank you very much.